Electric Motors by Noah Serafin.
Alexei Skunev.
And Amal Haggaday.
Electric motors are important because they are found in many things around us that relate to technology, including, but not limited to, the fan,
The radio.
And the TV. Magnetic fields are very similar to electric fields. Magnetic fields travel from north to south, while electric fields travel from positive to negative. To understand electric motors, we need to go over two basic concepts: ferromagnetism and ferrimagnetism. Both of these are a result of the phenomenon where certain metals' unpaired electrons align to form a permanent magnetic field. They can stay magnetized long after being within proximity of a magnet and can only be wiped either through time or through thermal agitation. Heating these metals to the Curie point will wipe away any ferromagnetic properties. Ferrimagnetic properties are similar to ferromagnetic properties, except not all of the electrons line up in the same direction. Some can be off at different angles. Some popular ferromagnetic materials include cobalt, iron, nickel, and some rare earth elements such as neodymium.
A basic electrical current is sent through a magnetic field, and as the current is carried through the loop, each side experiences opposite forces, the north and the south, in an electric motor. So essentially, in an electric motor, you have a battery or a source of voltage that goes through a loop that charges the coil, as this is the coil. And then as that is charged, the magnets on each side are going to pull it that way, push it up and pull it down, and so that creates a current and then a force and torque and so on and so forth. There has to be a slight force applied to start a basic motor according to Faraday's law of induction, which will be covered later in the video. However, more complex and less basic motors in the real life have multiple points in their coils, and so that whenever they rotate, they don't get stuck, and there's a more constant flow of the magnetic forces acting on the coil or the loop.
Now on to Fleming's left-hand rule. If a conductor carrying a current is introduced to a magnetic field, a force is exerted on said conductor. This force is perpendicular to both the direction of the current and the orientation of the magnetic fields. In 3 dimensions, it can best be modeled like this: a hand that's shaped like a gun. The middle finger represents the direction of the current flowing from positive to negative. The pointer finger represents the direction of the magnetic field traveling from north to south. And the thumb represents the direction of the force.
So this is a diagram of an electrical motor, and what this consists of is 2 magnets, a commutator, and electrical current through these wires. Pretty much how the torque is made is when the current is moving through the wires, and when there's a current moving through an electrical field, a torque is pushed down on a wire, which is perpendicular to the electrical field and the magnetic field. And this can be seen by this equation: force equals QV times B, where X is the cross product. Another important phenomenon is magnetic flux, and it is the surface integral of the normal component of the magnetic field, B, passing through the surface. And the equation for magnetic flux is the double integral of B times ds, which is the sum of the magnetic flux over the surface S. And the unit for flux is Weber, volts per second. And you can see a diagram how this surface integral works is that it takes the sum of all these vectors, and combine them together, and that's how you get volts per second.
And so another part of the electric motor is the commutator, which would be this part. So the commutator consists of brushes, and for the brushes, basically when the coil becomes 180 degrees, or so the coils are that way, they become basically straight up and straight down, perfectly perpendicular, and so the brushes are gonna used as contact points, and the brushes will come off, and this is going to allow the reverse of the current in the motor, so that instead of reversing the torque every time the coil moves through the plane, the brushes, when they come off, just keeps the coil rotating, and since the brushes come off, the momentum carries the coil through, so that the current can continue and the torque will continue, and their voltage will be constantly produced.
Another important concept in electrical motors is Faraday's law of induction. Pretty much what it states is any change in the magnetic environment of the coil of the wire will cause a voltage to be induced in the coil. Pretty much whenever this coil moves around, there's voltage produced inside the coil, which will induce a current going into the coil, and this will make torque within this electrical motor. And this is why a current is able to flow in a motor, because the surface area of this commutator changes a little bit, which makes the commutator spin a little bit. And here's a diagram of how this works. So pretty much when there's no surface area induced by the magnetic field, you get voltage of 0. So there'll be no voltage seen throughout this commutator. But when there's more surface area through this commutator, then there will be more voltage through the wire, therefore making more current within the wire. Afterwards, and this is how you see the equation through integral format. So pretty much voltage equals the line integral E times dl, and the line integral of the electrical field around a closed circuit loop is seen by this equation. And this is equal to negative integral of E of the surface times partial derivative B divided by partial derivative T times dA. And pretty much the important thing about this law is this part, because this is the part that changes, and every time there's change within this part, this changes the voltage, therefore making the electrical field actually work within this motor, therefore making more current within the motor, therefore making more torque within this motor. And
so we want to show you guys an example of this. So this is our own homemade electric motor, and basically what is going on here, you have your magnets at the bottom, which create the magnetic field. Then you have your battery creating the current, and then you have your coils on top. So according to Faraday's law, we're going to slightly push it, and when you do that, it then begins to spin at a good rate. However, since we don't have the greatest magnets, they don't spin as what you would expect, but that is our best example.
yeah, thank you.